Irish wish wish Irish wish raw Irish wish Irish wish Irish wristwatch Irish wish raw Irish wish
Science guy. Do you notice that the planets that are closer to the sun move about it much more quickly than those farther away?
Gravity is the glue that holds our solar system together. Gravity pulls on the planets and keeps them in orbit, the same way this rope pulls on this ball.
It actually takes Mercury, the planet closest to the sun, only 88 days to go completely around it.
Now, when planets are close to the sun,
that's about as long as your summer vacation.
They spin around faster than when they're farther away.
Our Earth goes about the sun once each year.
That's because even though they're going fast, they have a longer distance to go when their orbits are bigger.
And the planet farthest away from the sun, Pluto,
you with me?
Naturally has the greatest distance to travel.
You see what I'm saying?
It makes the trip around the sun in about 248 years.
You with me? Okay. Oh!
All of the stars, including our sun, give off their own light. But a few of those bright spots in the sky are not stars. They shine only because they reflect. They are called planets.
Hi, folks. Looney Worthington of Looney Worthington's Miles and Moons, ready to make you a deal that is out of this world on moons. From the one that started it all, the one that causes the tides, the one that goes around and around the Earth, the moon.
The moon looks like the biggest thing in the sky, doesn't it?
No magnetic fields, no signs of life, no water. Hey, this baby's ready to sell.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy.
Imagining distances in space is difficult because everything is so far apart. But think of it this way. Let's say that this miniature soccer ball is the size of our sun, and it's right on the goal of a soccer field. Then this speck is Mercury. This is Venus. This tip of a ballpoint pen is our Earth, 2.5 meters from the miniature soccer ball sun. Mars, Jupiter, Saturn, 25 meters from the goal. Uranus, and Neptune, 76 meters away. And Pluto's back here, almost out of the building, 100 meters away. How far do you think it is to the next star? Well, it's not in here.
Kids, don't drive this way at home. You could leave tire marks on the living room carpet.
Boy, I hope I unplugged the iron. Hope I didn't leave the stove on. It would be here. The nearest star would be here. 7 hours of highway driving, about 700 kilometers away. And that's only if you think of the star as being this big. I mean, real stars are huge, enormously huge,
Right.
enormously, bigly huge.
All right, already.
Nothing like this. You couldn't get to the nearest star if you traveled your entire lifetime. No way. It's kind of cold out here.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy.
Just like the airplane that seems small when it's far off in the air, but is really big when you see it close by on the ground, the sun only looks small because it is so far away. In fact, the sun is so large it would take 109 Earths strung end to end to equal its diameter.
That's because the sun is big.
And the sun is hot, reaching temperatures of about 15 million degrees Celsius at its core.
See how my head is blocking the sun?
Whoa, you're so...
Things happening with the moon right now. The moon is blocking the sun. Here's how it works. The sun is up there, right?
Hopefully.
Then the moon casts a shadow on the Earth. And that's an eclipse. See the round shadow of the moon? That's all there is to it. It's a solar eclipse. Whoa, look at that thing! Whoa, look, you see it just perfectly! They laughed at me! They laughed! Ha! Oh, hi. Just looking at the sun with a pinhole viewer. See, you should never look at the sun directly. You can hurt your eyes. Here's what we have. We've got a white piece of paper taped to this end of the box. Then at this end, we've cut a small hole, see? Then on the outside, taped a piece of aluminum foil, and using a pin, I poked a small hole. That hole makes an image project through the box onto the paper. And you can observe the sun or a solar eclipse easily. Take a look. See? It works great.
Bill Nye the Science Guy.
Slow, you're so...
You're so mentally and physically.
Everybody quiet down because I played these games before.
Okay, yeah, we should listen to
I
him.
have.
Okay, he played these games before.
I'll give you $10.
The $10 dollar?
No. That's it. I'm blowing you up and when we get into a fire damp room. We're gonna follow, bro. Over here. Bro, what are you doing? Bro! lasted only 36 seconds. Okay. It's this one, guys. Don't trust the guard. Guys, never trust the guard. It's not...
This is too much chaos for I cause chaos.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy.
Now, suppose we want to make a big static electrical charge. Well, we could use something like this. This is called a Van de Graaff generator. It's named after Robert Van de Graaff. So here's what happens. Electrical charges are deposited on this rubber belt. The rubber belt turns and redeposits the electrical charges up here on this metal ball. Now, since this next part of the demonstration rocks, I'm gonna put on my rocker wig of science. Yeah. Now, start the rubber belt turning. Electrical charges are being deposited on the metal ball. They're running through my arm and being deposited in me. And look, it's building up in my rocker wig of science. See, since these charges are all the same, they're not attracting. No, they're repelling. They're pushing apart. So they're pushing the hairs of my rocker wig apart. Now, if I could find a way to get these electrical charges off of me back into some other parts of the room, the hairs wouldn't repel each other. There wouldn't be a static electrical charge. No, the charge would jump. Let's try it. Watch what happens when I bring this ball near this ball. See the spark? The charges jumped. The static electrical charges aren't static. No, they jumped. Static electricity. It rocks. See that? It sparked.
Bill Nye the Science Guy.
Trailer, take two. Trailer, take two.
Oh!
Trailer, take two.
Oh my days! And there's so many different ways to skin the cat.
I already got my lunch. Thanks for the invite, but
You are the key to my problems.
Botzeborg, this walk is taking forever. Are we almost there?
We are finally here, let's go.
What is this?
Cyborg, this is Tower of Terror.
Oh, guests. Hello, hello. My name is Ghostface. Welcome to Tower of Terror.
Why does lightning strike every time someone says the name of the ride?
No reason. Good luck.
Oh, okay, let's go.
Oh yeah, I forgot to tell them whoever rides this never returns.
Am I the only one who thinks there is something off?
Well, too late to back down now.
I can't take this anymore. Let it end. Let it end.
I'm literally throwing up over here.
Are those ghosts? Well, Botzeborg, I think I learned I'll never be doing that again.
Same for me.
By the way, where are we at? Oh, we are at Dino Land.
I'm sorry, but I can't let you free anymore. After what you did... Oh, someone is calling me. I better check who it is.
Wow, so the rumors are true. There really is a door here. I prank called Ghostface so I could get past him. Time to open.
Stop. You don't know what you are doing.
I need to see if the rumors are true.
But that will release. Oh, that must be our guests. Don't open that door and stay here. Oh, hi guys, I'm glad you're here. I need help with the lab. You guys can explore for a bit while I have my small coffee break.
Let's check out the rumor of Door 99. Time to see if the rumors are true.
Wait, stop.
Well, what happened? Oh yeah, I opened Door 99. And now where am I?
Bro, this is the easiest game I've ever played.
Hello!
Hey, someone opened door 99, and he is now stuck with 1 by 1 by 1.
Don't worry, I know how to save him. Just lemma defeat dam, seek real quick.
Okay, sounds good.
What in the world happened? Ever since that 1x1x1x1 guy got me, now I look like this. And where even am I? Guess I'll go explore and find out.
Well, this is the place Cyborg went to when he got sucked into door 99.
Can we keep moving? I'm scared.
Wow, this place is insane. It just keeps getting bigger and bigger. Look, there are 3 buttons. I guess I'll try the blue one first. That was weird. Now I'll try the green one.
Bro, that didn't do anything.
What in the world? Okay, I guess I'll try the red one. What did that do?
Hello, is anybody here? Oh, 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 oh.
These places just keep getting weirder and weirder. Will this 1x1x1x1 guy ever stop?
Look at Cyborg. I told you my GPS would work.
It is that what happened to him.
It was that 1x1x1x1 guy, he turned me into this outfit.
Oh, wait a minute, this makes sense. 1 by 1 by 1 by 1 turns people into something called classic, and if you have been turned classic you cannot leave door 99. However, I have learned a lot about 1 by 1 by 1 by 1. We can stop him, but there is a chance you might be stuck here forever.
Let's try.
Oh, door 99 has been opened now. I'm in it. What am I gonna do?
I think I know what to do.
So are you gonna explain who you are and how we can escape?
You are not leaving till you help me take 1 by 1 by 1 by 1 down.
Who the flying chimpanzee is that?
Me and him used to be friends, let me explain. Me and him worked in the void together, that was before he became the hacker he is now. 1 by 1 by 1 by 1 was a test experiment made by scientists, but the experiment failed and he broke loose. He made his own realm and it got out of control. He soon took over different myth places as of the Bermuda Triangle, Tower of Terror, and of course door 99. Is there anything else we should do, sir?
No, keep it like this, it's perfect.
1 by 1 by 1 by 1 used to talk a lot back then, now he doesn't really talk at all.
You stay here, I want to check out what is outside door 99 and see what it is like. Well, I definitely wasn't expecting this.
Wow, so the rumors are true. 1 by 1 by 1 by 1 is living in my door. I created wow.
Well, so much I can take over.
I think I'm just gonna lock the door.
And as you guess, that's how this all happened. That's how he locked door 99, and now one by one seeks revenge. I haven't left in a while and he has lost it. He must be stopped now. Anyway, that's my story.
Wow, that was intense and sounds like you put up quite a showdown.
I did, LOL.
But I need to save my friends. I can't focus on taking down one times one right now. I'm sorry.
It's okay, I understand, and I want to help your friends too. I just wish there was somebody out there who could help us out in the real world. My tracking device says he is somewhere over here, but I don't see him.
This place is kinda cool. Where are we exactly?
I'm not quite sure. I haven't seen this one yet.
Hey guys, I found 2 people over here. Come.
What?
Oh my gosh, you found Botzeborg.
Who?
My cousin.
Oh, right.
And who's that guy?
I am Salty. I used to work with one by one, but now I want revenge on him, and to save you guys.
How about we all split into 2 and try to find 1 times 1 times 1 times 1?
What in the world is this place?
Well, it looks like Sharkbite 2.
Nah, 1 by 1 by 1 by 1 and water just don't go along together. Let's go.
Wait, I want to come. Ugh, never mind.
Nah, is this Primal Pursuit? This is not our place. If there's dinos, then 1 times 1 times 1 times 1 wouldn't step a foot here.
What just happened?
I'm all by myself, lame. Or are you? Hello, Salty, we finally meet. Who are you and where is 1 by 1 by 1 by 1? I go by Pain Mills, however here is something I noticed. You want all the attention, and to be the hero, however that ain't happening. Just let me defeat him. I haven't been on the show since episode to see Mom. I ain't gonna ask you again. Move out of the way. No.
Shadow, but after everything you did, you must die.
But Shadow, I just wanted to stop the humans from destroying our dimension until you turned against me.
Wait, really? But wait a minute. They weren't attacking our dimension.
They were just let me live, and trust me, Shadow, please.
No!
Well, this is the end for me. Guess I won't live to be a great villain after all. How am I still alive? And who are you?
My name is hidden for now. Who are you? I could feel a powerful feel from you.
My name is King Shadow.
That is not important right now. I just took over door 99 with my pal Salty, and I need some help.
As long as I'm still alive, we have a deal. Well, what is this place?
That is not important. Tell me more about you.
Why do you want to know so much about me? Tell me your name first at least.
My name is 1 by 1 by 1 by 1. Happy?
Yes, now then I will explain who I am. I'm King Shadow. I was defeated by someone named Cyborg 99 and his friends.
Wait, Cyborg 99? Salty talks so much about him. Let me see where he is right now. It says Cyborg 99 is on a ride called Tower of Terror. I'ma go ruin it for them, ha ha ha.
We're the best team. Hey, get away. I want to make a deal. Help us defeat Cyborg 99 for maybe a reward.
Ghostface, look at Salty. We found him.
Indeed we did, but he looks weak. What happened, Salty?
Some guy named Tane Mills came up to me and wouldn't let me pass.
Did you find 1x1x1x1 yet?
I have not, but I think he is somewhere around here. We could try looking back at his office.
All right, let's go.
We will be safe here, sir. I have no clue where we are, but they won't find us. Now then. Where is Tane Mills?
Bro, nobody has found 1 by 1 by 1 by 1 yet. It's like he vanished. Bro, what is that?
Well, here we are, his office.
Cool, but I don't think he is here. Where could he be?
Oh no, not this guy. Everyone, let's get revenge.
I hate chases, but thank goodness we escaped. Who even was that guy? Oh, you have got to be kidding me. Well, at least we found him. Oh shoot, we are cooked. What was that? My head hurts from that big explosion.
It appears he has failed, sir.
It's fine. We can do this by ourselves. Say goodbye.
Oh hey guys. I lost Ghostface and Salty. Have you seen anyone?
Only this guy.
Ray.
It seems I have stumbled into the purple void.
Indeed you have. Now time to die.
Wait, is that 1x1 axe 1x1's sword?
Yes, I took it to have a better chance at winning this fight.
Well, look who it is. How's the fight?
Terrible. He was really smart and got the sword. We gotta be careful.
You took my sword without permission. I will take yours as a replacement.
But sir, my sword isn't even that good.
I don't care. You haven't helped me at all. I can do this all alone.
we proudly present to you the Kurzgesagt Guide to Curiosity. Join us on an interactive adventure across 160 thrilling pages that will change your perspective on the world forever. Available now on the Kurzgesagt shop. You might be inside a black hole that's inside a black hole that's inside a black hole. Everything in existence could be black holes all the way down. It turns out black holes are much weirder than you think, and they break the universe much more than is usually explained, destroying time and space. And they may actually create infinite universes in the process. But before we can get to that, let's first build a black hole out of air. Everything can become a black hole if you squeeze it to a critical limit. You'd need to squeeze Earth down to the size of a coin for it to turn into a black hole. The Sun needs to be squeezed down to the size of a small city to become a black hole. And if a lot of mass is concentrated in a really tiny space, you get something super dense. This is usually how black holes are explained. Stuff becomes super dense and collapses into a black hole. But actually, you don't need any ultra-dense stuff to make them. We're ignoring some maths here, but all you really need to know is one thing. The larger black holes get, the less dense they are. So, really large black holes are kind of thin. A sun mass black hole is only about 6 kilometers wide and has a density of about 1 Himalayan range per cubic meter. The supermassive black hole at the center of the Milky Way has a mass of 4 million suns, a diameter of 24 million kilometers, and a density of 6 blue whales per cubic meter. The ultramassive black hole Iris 2100-4156 has a mass of 3.8 billion suns and is as wide as the solar system. But because it's so large, it is only as dense as air. This means, at least in theory, that if you take a gigantic balloon and fill it with undecillions of tons of air, the moment it gets to the size of a solar system, an event horizon suddenly forms and it turns into a supermassive black hole, without violence or squeezing. So now, let's think big. What do we need to make a black hole the size of the universe? A universe-sized black hole. The chunk of the universe that we can see from Earth is a sphere with a radius of 45 billion light-years, filled with hundreds of billions of galaxies, lots of gas, and a bunch of other things. If you add them up, it has the mass of about 1 billion suns. Which sounds a lot, but on average, the universe is not very dense. If we break up all the galaxies, stars, gas, and energy and spread them equally inside the volume of the universe, we get an average density of about 5 hydrogen atoms per cubic meter. You can imagine this as the sort of ultra-thin cosmic air that makes up the universe. What would happen if we take a balloon as big as the observable universe and fill it with cosmic air? Well, it turns out that all the mass in the observable universe is more than enough to create a black hole. Actually, it's enough to make a black hole 10 times larger than the observable universe. But that can only mean one thing. We should be living deep inside a truly gargantuan, cosmic-sized black hole. There's one catch, though. We know that our universe is expanding, and an expanding universe is not what you'd expect to see if you were inside a black hole. So our universe can't be a black hole, at least not in the naive way we've just described. Except there's a wild and mind-bending trick the universe could play on us. To find out how, let's jump into a black hole and die. A whole universe born inside a black hole. We usually imagine black holes as spheres with a singularity at their center, a point where all their mass is concentrated so much that our maths breaks down. But this is a lie. They are so much weirder. From the outside, a black hole looks like a normal black sphere, but the inside is where things stop making sense. Black holes warp the universe so much that at the event horizon, space and time switch their roles. Inside a normal sphere, space is finite, but time goes on forever. But inside a black hole, it's the other way around. Space goes on forever, but time is finite. So once inside, you see an infinite universe with no center. The geometry is too complicated, so we're simplifying. But basically, you could walk forever in one direction, or walk in another direction and arrive at the same place again. But not only that, inside a black hole, time is finite, and it's now running out. So after a while, you start to notice that space itself is slowly changing. In one direction, space is being stretched, while in all other directions, space is shrinking. The whole universe is being squeezed, kind of turning into a collapsing spaghetti. Sooner or later, the whole black hole universe collapses into itself. All of space, every single part of it, is turning into a singularity. So the singularity of a black hole is not at its center or in any direction at all. It's in the future of whatever falls inside. We made a whole video about this if you want to learn more. So the singularity is not a place where you can go, it's an event in time that happens. Once it happens, you and everything else that fell inside the black hole will be mercilessly crushed into an infinitely small region with infinite gravity and infinite energy. Time, space, none of it matters anymore. Both kind of stop existing in ways that we would recognize. And then, is this the end? Well, maybe not. This collapse of the black hole universe into a singularity looks like one of the scenarios for the end of our universe, the Big Crunch, where long after the Big Bang, the whole universe collapses into a singularity again. But if there's a big crunch, there might be a big bounce, like a rubber ball that you've squeezed too much and that suddenly rebounds. Space might expand again. So a new universe could be born inside a black hole. The funny thing about this scenario is that nothing has changed in the slightest outside the black hole. Watching from the outside, it's still a black sphere of nothingness. And yet, on the inside, a new universe has been born. So maybe our universe was born like this, and we are all actually inside a black hole. But if our universe can also create black holes, they might give birth to new universes. Is our black hole universe also just part of a universe further up that's also a black hole inside another universe? Is there an end to it? Is there one original universe? Is the cosmos black holes inside black holes inside black holes? Infinite black hole universes. If the universe creates black holes that create universes, that then create new black holes that create new universes, this cosmic self-reproduction would be subject to natural selection. A Big Bang is a chaotic and messy event, so it's possible that the new daughter universes would not always be fully identical to their mums. Sometimes physics may be slightly different, with some fundamental values higher or lower, and so some universes might be able to create loads of stars, planets, and black holes. Others might not, maybe creating a uniform cosmic soup where no stars, planets, and black holes form. But if all universes are born inside black holes, in the long run, all universe lines that don't create loads of black holes would die out. The universes with the conditions for loads of black holes would become the most common and spawn the most daughter universes. Survival of the fittest, but with universes instead of organisms. Our observable universe alone has created at least 10 to the power of 17 black holes so far. So maybe our universe has the physics and laws it has because it was born after a long process of cosmological selection that favored the production of tons of black holes. And that would have a lovely side effect. If universes are optimized to create as many new black hole universes as possible, they're optimized to create loads of galaxies and stars. And thereby also, by accident, the conditions for life to emerge. So universes that are the best at creating new universes are also the best at creating life. If this scenario is true, who knows how many bazillions of black hole universes might be out there, all with stars and planets potentially home to others like us. So, is our universe like this? The truth is we don't know. While these ideas are based on real science and work on paper, they're speculative and not testable. Also, cyclic universes don't actually explain why the universe exists in the first place or why it is the way it is. Instead of providing answers, these are really just new questions in disguise, so keep that in mind before getting too excited. But isn't it just wonderful and heartwarming that we're living in a universe where ideas as big as this one are even thinkable? There might be so much life. And if new universes are created constantly, maybe life will go on forever. We've heard rumors of a chosen one, a special verb who has the power to illuminate the vast darkness of the universe, uncovering the great mysteries of the world. This special power is called curiosity.
Hi, you're on a rock, floating in space, surrounded by more rocks, and gas, and a bunch of nothing, mainly. Oh hey, look at that, the rocks are going around the gas. Hold on, what the heck is going on here? To understand, let's look at a little bit of physics. Wait, did I say a little bit? To find out what kind of magic this is, we'll have to go back in time. Okay, not that far. Stop. Yeah, that's perfect. This is Gravity Guy, but most people call him Isaac Newton. One important thing he said is that force equals mass times acceleration. Now, what do all these words even mean? Force is a push or pull on something in a certain direction. Mass tells you how much of something there is, and it's also a measure of inertia, but we'll get to that later. And acceleration is the derivative of velocity with respect to time, but that's too many big words for my taste, so let's just say it's how fast your velocity is changing. The key takeaway is that if you apply force to a fixed mass, you get a predictable amount of acceleration. If you know all the forces acting on a basketball midair, you can predict with 100% certainty if the ball will go in the hoop or your neighbor's windshield. Whoa, did an apple just fall on my head? Yes, Newton, it did. Yeah, that must have happened for a reason, said Newton, as he discovered that two masses attract one another, making the apple fall. Yes, even you, no matter how ugly you think you are, attract pretty much the whole universe at least a little bit. Hey, can you put that on paper? Yup, said Newton, who gave us the law of universal gravitation. In other words, how much do bodies pull on each other given their mass and distance times a constant. Bigger mass, bigger pull. Bigger distance, smaller pull. Actually, a lot smaller pull. You see, as the distance increases, the force gets smaller by the square. That, my friends, is the inverse square law. Gravity is also the reason why planets in our solar system orbit the sun. They got their initial velocity when the solar system formed out of spinning gas, and since there's nothing in space to stop them from moving, they'll keep moving. Hey, that's Newton's first law. The sun is so massive that the force of gravity keeps pulling the planets towards the sun, but the planets are fast enough to essentially fall towards the sun but miss it, and this goes on forever, creating a round orbit. Actually, that's kind of a lie. Most orbits are not perfectly round, but more egg-shaped, and Pluto's orbit is just a complete mess, but you get the idea. In this case, the gravity is what we call a centripetal force. One thing many people confuse is mass and weight, and no, they're not the same. Mass tells you how much of this blob there is, and weight is the force of gravity the blob would feel. To make things clear, your mass would be the same on the Earth and on the Moon, but the weight you would perceive is different because the Moon has a weaker gravitational pull, meaning a weaker force acting on your mass. So really, you're not overweight, you're just on the wrong planet. Alright, enough about Newton, let's break some stuff. If you ever dropped your phone, it might look like this. What the hell, ground? Why'd you do that? The answer is energy. You know, the thing kids have after eating gummy bears. Energy has the unit joule, and it's not like force. It doesn't have a direction, it's just a number that's kinda chilling there as a property of a thing. You see, there's two main kinds of energy, kinetic energy and potential energy. In plain English, energy of movement and stored energy due to some circumstance. For example, when you held your phone, it stored gravitational potential energy due to being held above the ground at a certain height. Once you dropped it, that potential energy was converted into kinetic energy as the phone fell. Then it smashed into the ground, and the phone absorbed some of the energy, making the screen go boom. Work is defined as force applied over distance. For example, if you lift an apple by 1 meter, you would have done about 1 joule of work. This happened by converting chemical energy stored in your body to gravitational potential energy stored in the apple. As you may have noticed, energy and work have the same unit joule, so they must be the same thing? No, energy is the total amount of work that a thing could possibly do, and work is just the stuff that actually happened and required energy. If you try to lift a weight that's too heavy for you, you'd feel like that took a bunch of work, right? Well, yes, but your feelings are invalid in the face of physics. Mathematically, no work has been done, because work is force applied over distance, and since you didn't move the weight at all, no distance means no work. The key thing to remember about energy is that it cannot be created or destroyed, only converted, aka the conservation of energy. Okay, but a car that's moving has kinetic energy. When the car stops, assuming the car doesn't smash into a wall, where does that energy go? When you apply the brakes, there's friction between the brakes and the wheels, causing the car to slow down and creating heat as a byproduct. That heat is then dissipated into the surrounding air, and that makes the molecules in the air move faster. Things that move have kinetic energy, so ultimately the kinetic energy is transferred from the car to the air. With this knowledge, we can define that temperature is just the average kinetic energy of atoms in a system. You see, all atoms, not just molecules in the air, wiggle, like this. The faster they move, the hotter things get. That is temperature. All that talk about hot stuff, I think it's time we talk about thermodynamics. It tells us that jumping in lava is probably a bad idea, but more importantly, the absolute mess that is entropy. Literally, it tells you how much disorder there is in a system, indicating the number of possible states a system could be in. For example, get an ice cube, no, not that one, yeah, that's perfect, and put it in the sun. The sun will obliterate the ice cube and turn it into water. Looking at the structure of ice and water, we can see that ice is more neatly organized than water, which just kind of goes all over the place. Also, the water could look like this, or even this, but the ice will always look a little something like this. In total, the system went from low entropy to high entropy, meaning more disorder and more possible microstates. This trend applies to everything. The whole universe is on an unstoppable path to higher entropy. It's also the reason why time seems to only go forwards. Practically, entropy tells us that some forms of energy are more useful for doing work than others. Burn some gasoline and your car will move, spitting out heat and gas. That heat and gas is pretty much gasoline, just in the form of higher entropy. And as you can imagine, this stuff won't really make your car move, and the gas won't spontaneously turn back into liquid gasoline, meaning the form of gasoline with lower entropy is more useful for doing work. Okay, but if you put some water in the freezer, will it not decrease in entropy? Yes, but the fridge is not an isolated system and will heat up the room more than it will cool down the water, increasing the total entropy. Want to see some magic? Whoa, what just happened? Some electrons apparently moved through some wires and let there be light. What is going on here? Objects have a fancy something called a charge. It can be positive or negative, or if you have the same amount of both, an object is neutral. Electrons have a single negative charge. The flow of electrons is called electric current. To describe it, we use 3 parameters: current, voltage, and resistance. Current is the amount of electrons passing through a wire in a given amount of time. Voltage is what pushes the electrons to move, but simply put, it's a difference in electric potential, so you can imagine it as a slope that goes from high potential to low potential, where the flow of current goes downhill. And resistance is pretty self-explanatory. This is Coulomb's law. Wait a minute, this is just Newton's law of gravitation in disguise. This tells us that electric charges attract each other in a similar way masses do. Opposites want to cuddle, while like charges literally couldn't think of a more disgusting thing than to be with one another. These four equations explain pretty much all of electromagnetism, but don't be scared just because they look scary. I mean, yeah, they do, but it's simpler than it seems at first. The first one states that if there's an electric charge, there will be an electric field, or this big E, emerging from it. Add another and you have an electrostatic field. These lines tell us in which direction a charged particle would feel a force at any given point. The second one tells us the same for magnetic fields, and even though electric charges are cool and can be alone, magnetic poles are not. They're very lonely, and there will always be a north pole together with a south pole, and a single pole can never be alone. Okay, now here's where things get kinda freaky. You know how electric charges only act on other charges and magnets only affect other magnets? Well, that's only true if they're not moving. The third and fourth Maxwell equations tell us that a moving magnet creates an electric field and a moving charge or electric field creates a magnetic field. One consequence of this is that current can seemingly come out of nowhere by moving a magnet next to a conductor. The moving magnet creates an electric field which makes the electrons inside the conductor go crazy. That is called induction. In other words, electric and magnetic fields are so tightly linked that they are two parts of the same bigger thing. Let's say we have a charge. Since it doesn't move, it has a static electric field. If we accelerate the charge, there will be a magnetic field around it. That magnetic field interacts with the electric field, which again changes the magnetic field, and this is a sort of chain reaction that makes the electromagnetic field radiate outwards into space as an electromagnetic wave. Depending on the frequency, the human eye can actually see this. It's called light, but most of the spectrum is invisible to the human eye and is used for things such as Bluetooth, wireless charging, and confusing human apes into thinking magic is real. Hey, can we go back to the water and look at those molecules? Yeah, those. What are they made of? The molecules are made of atoms. Atoms are made of a core and some electrons. The core is made of protons and neutrons, both of which are made of quarks. They're strange yet charming from up top down to the bottom. Oh yeah, there's some more stuff, like for example the overweight brothers of the electron. All of this together makes up the Standard Model, which we believe to be the smallest things in the universe. At least that's the excuse we have for not knowing what quarks are made of. Fun fact, depending on the number of protons in the core, you get different elements. Depending on the number of neutrons in the core, you get different isotopes of the same element, most of which are a little overweight and very unstable, so they fall apart into smaller atoms. That releases ionizing radiation. Not so fun fact, that stuff will kill you. If you have a large group of atoms, you can predict when half of those will have fallen apart. That's the half-life. Depending on how unstable an isotope is, it will survive a certain amount of time. Some don't want to live, some really don't want to live, but some will live far longer than you probably will. Oh yeah, did I mention that light is like the fastest thing in the universe? To be exact, 299,792,458 meters per second in a vacuum. That is pretty fast, said everyone. Also, light is a wave, said everyone. Why? If you shoot it through two teeny tiny slits, it creates a fancy pattern due to interference, which is just a wave thing. You see, when two waves cross, they can add up or cancel each other out. These gaps are the spots where they cancel each other out. So in this case, light behaves like a wave. Nah, screw that. Everything you know is wrong, said Albert Einstein, probably smoking crack after hearing about the photoelectric effect and discovering that light comes in tiny packets called photons. I sure hope that doesn't unravel a whole new area of physics. Anyway, he said, as he continued to casually drop an absolute bomb on the entire field of physics with his theory of relativity. He assumed the speed of light is constant because it arises from two other constants. He also assumed the laws of physics are the same for everyone, regardless if moving or at rest. Now think about it. If two people turn on a flashlight but one person is standing still while the other person is on a moving train, wouldn't the person standing still see the other person's light as going faster than the speed of light? The reality is, no, it would be the same as their own flashlight. That's impossible, except if time passes slower for that person from the perspective of this person. In other words, if the speed of light is constant, time must be relative. Also, gravity is not actually a force, sorry Newton, but rather a consequence of masses bending space-time. Einstein thought the universe is a mesh of space and time, and anything with a mass bends this fabric. Also, all objects move freely on a straight line when moving through space. Gravitation is simply the result of objects following these bent lines which appear straight to them. If you have a hard time understanding this, you can imagine two people on Earth walking in parallel straight lines. Now imagine one standing on the east coast and one on the west coast of the US. If they both walk north, eventually they'll meet at the North Pole. Because of the curvature of the Earth, they ended up at the same point even though they both walked straight relative to themselves. Oh yeah, by the way, energy and mass are kind of the same thing, he added, which explains why atom bombs are so freaking powerful. According to this formula, even just tiny atoms can release a humongous amount of energy by giving up just a fraction of their mass during fission. What is fission? It's the same thing Oppenheimer used to make this thing go boom. You see, there's two main ways to gain energy from changing nuclei, fission and fusion. Fission aims to split the nucleus of an atom into two or more smaller nuclei, which is most often achieved by blasting the core with neutrons. Fusion is the opposite, where you combine two smaller nuclei to get one bigger one. The energy came from something we call a mass defect, where the resulting nucleus is lighter than the starting nuclei. This missing mass is what was converted to energy during fusion. Fission and fusion are cool, but you gotta be careful or you might just blow up the planet. That totally didn't almost happen before. Multiple times. Hey, remember when Einstein said light is a particle? He accidentally discovered a whole new field of physics which he thought is just a giant hoax. Quantum mechanics. This stuff is crazy. Another German guy called Max Planck said, yes, Einstein, you're right. Light does come in tiny packets. Actually, all energy comes in tiny packets, or quanta. Want to know where an electron is inside an atom? It's here. And there, and everywhere at the same time, actually. That's a superposition. It's not in one state, it's in multiple states at once, at least until you measure it. Then it chooses one cozy spot to be in. Schrödinger gave us an equation that gives you a probabilistic model of where you can find it if you were to measure. You can imagine this as a cloud, and the denser it is, the more likely it is for an electron to be there. But still, where exactly it will end up once you measure it is random. Speaking of observing particles, they're also super sensitive about their private data. Look at these two images of a flying ball. In one, you can clearly see where the ball is, but not in which direction it's moving, and in the other, you can see where it's moving and approximately how fast, but not where exactly it is at the moment. That is essentially Heisenberg's uncertainty principle. You can never know both the exact position and the exact speed of a quantum particle at the same time. Okay, let's recap. A small thing can be a particle and a wave at the same time, and when we try to look at them, weird stuff happens. But you know what? It gets even weirder. Think back to the double slit experiment. We know that a light beam acts as a bunch of waves and we get interference. But here's the weird thing. Even if you send individual photons after sending enough of them and detecting where they end up, you get interference. Like, how can that be? What did a single particle interfere with? Well, we think it interfered with itself because it acted as a wave and went through both slits at the same time. That's a superposition. Okay, well, let's just measure which slit it goes through. Yeah, that's not gonna happen. Once you start measuring which slit the photon goes through, it stops acting like a wave and the interference pattern disappears, as every particle chooses just one of the slits to go through. Sounds kinda suspicious to me. Anyways, all this knowledge is going to cost you one subscribe and a thumbs up. Thank you very much. And you can decide if maybe you'd want to tip with a comment, perhaps? Computers make no sense. Throw some metal in a box and boom. What the heck is going on here? Inside your PC is a central processing unit, or CPU. It's basically just a piece of silicon with billions of microscopic switches called transistors. Depending on the flow of electricity, they can be on or off, kind of like a light bulb, which gives us two states, 1 and 0. The value at one of these switches is called a bit. One bit by itself doesn't really do much, but put them together and A group of 8 bits is called a byte and can have 256 different combinations of zeros and ones. Congratulations! We can now store information by counting in a system called binary. Every bit represents a power of 2, 1 meaning the power is included and 0 meaning it's not. So this number has 1 times 64, 1 times 4, and 1 times 1, which adds up to 69. This is nice, but for humans, hexadecimal is even better. It's often denoted by the 0x and is simply a more readable format than binary. 4 binary bits can take any value from 0 to 15. Hexadecimal uses 0 to 9 and A to F to represent those values, so a group of 4 bits can be replaced by 1 hexadecimal digit. Okay, now that we can store numbers, we just need the computers to actually, do something with them. Using transistors, you can make logic gates, which are electronic circuits that encapsulate logical statements. You can think of it as a light bulb with 2 switches, where the light only turns on under certain conditions, for example, only if A and B are on. By combining logic gates in a clever way, you can build circuits that perform calculations according to Boolean algebra, which is a system formalizing mathematical operations in binary. But even though computers understand zeros and ones, for humans it's not really all that useful. So, using a character encoding like ASCII, we can assign a binary number to each character. When you type any on your keyboard, it gets translated into this binary code, and as soon as the computer sees this, it says, "Ah yes, that is a capital A," and slaps it on the screen. How these devices fit together is handled by an operating system kernel like Windows, Linux, or Mac, which sits between computer hardware and applications and manages how they all work together, for example with device drivers. Input devices allow you to give the computer instructions with the press of a button, but at the lowest level, computers only understand instructions in machine code, which is binary code telling the CPU what to do and which data to use. When it comes to following these instructions, the CPU is kind of like a genius, just with the memory of a demented goldfish. It can handle any instructions, but it cannot store any data, so it's only really useful with random access memory, or RAM. You can imagine it like a grid, where every box can hold 1 byte of information, which can be data or instructions, and has an address so the CPU can access it in 4 steps. Fetch from memory, decode instructions and data, and finally execute and store the result. This is one machine cycle. Since a program is basically just a list of instructions in memory, to run it, the CPU executes them one by one in machine cycles until it's complete. Oh yeah, did I mention that this happens really fast? Modern CPUs can do billions of cycles every second, which are coordinated and synchronized by a clock generator. The speed of this clock is measured in gigahertz, and people often overclock their CPUs to improve performance, which is nice but might just set your PC on fire. What's even crazier though is that a CPU has multiple cores, which can all execute different instructions in parallel, so at the same time. Each core can also be split into multiple threads, which allows every single core to handle multiple instructions concurrently, so switch between them really quickly. Okay, that's cool, but it doesn't matter how powerful a computer is if you have no way to give it instructions in the first place. Typing machine code by hand would probably make you go insane, but luckily, you don't have to. The kernel is wrapped in a shell, which is just a program that exposes the kernel to the user, allowing for simple instructions in a command line interface with text inputs. But the best way to make a computer do something useful is with a programming language, which uses abstraction so that instead of this, you can write code that looks like this, which is then converted into machine code for you. Some languages like Python use an interpreter, which directly tries to execute the source language, which you can interface with text inputs, so that instead of this, you can write code that looks like this, which is then converted into machine code for you. Some languages like Python use an interpreter, which directly tries to execute the source code line by line. Other languages like C or Go use a compiler, which converts the entire program into machine code before putting it in a file the CPU can execute. Now, every programming language has different syntax, but there's some basic tools almost all of them have. The most basic way to use data is with variables, which assigns a value to a name which can then be reused and modified. Depending on the value, variables can have different data types. For text, there's single characters and strings of multiple characters. For numbers, there's integers which can also be signed if they're negative, and floating point numbers for decimal values. They're called floating point because the decimal point can float around to trade off precision with range. This is possible because they use scientific notation. It's some number times the power telling you where to put the decimal point, which is exactly what they look like under the hood. The actual number is stored with binary fractions. Some fractions, like 1/3, can only be approximated in binary with an infinite sum. But since memory is not infinite, you have to cut it off at some point, which leads to rounding errors, causing pretty weird calculations sometimes. If these are not enough, long and double use twice the amount of memory to double the range of ints and floats. Some languages like Python automatically figure out which type a variable is, but in a language like C, you have to explicitly declare the type of a variable. The value of a variable is stored at some address in memory. Pointers are variables whose value is the memory address of another variable, which is denoted by this ampersand. So really, a pointer is just some chunk of memory pointing to another chunk of memory. Since a memory address is just a number, you can add and subtract from it to navigate through individual bytes of memory. This is called pointer arithmetic. In some low-level languages like C, you have to manually allocate and free up memory once it's no longer used. This all happens in the heap, which is a part of memory that can dynamically grow and shrink as the program demands, which allows for more control but makes it incredibly easy to completely break your code. You could touch memory you're not supposed to, or that simply doesn't exist, which is known as a segmentation fault. But also, if there's some chunk of memory that's no longer used and you forget to free it or you have no way to access it anymore, that memory is no longer usable. This is called a memory leak and can cause the program to slow down and eventually crash. To avoid this mess, high-level languages like Python have built-in garbage collectors that manage memory for you. Different data types take up a different amount of memory. Integers are most often 4 bytes of memory, a single character is most often 1 byte of memory, and a string is just multiple character bytes with a null character to signal the end of the string. Storing multiple items in a contiguous chunk of memory like this is the idea of an array. More generally, it's a list of items with the same data type, with each item having a numerical index, most often starting at 0. Since the items are next to each other in memory, by knowing the address of the first item, you can quickly index to any item in the array by using pointer arithmetic. Arrays are what's known as a data structure, which is just a way to organize data to make it easier to work with. Retrieving values from an array is blazingly fast, but the size of an array is often fixed when creating it, so when it's full you can't add anything, and if you don't use all of it, it's just wasted memory, so a more flexible option is a linked list. It uses nodes containing a value and a pointer to the next node, which allows them to be spread apart in memory. Also, it can grow and shrink dynamically as you can add and remove any node, and you can reorder it by simply rearranging the pointers. This is great, but they can be impractical as you have no way to access the last node except if you traverse every single one before it. But still, both arrays and linked lists are useful as they allow you to create queues and stacks. A stack follows the last in first out principle, just like taking a pancake from a stack. Practically, just imagine a pointer that always points to the item that was last added to the structure. Then you can pop, so remove the last item, which increments the pointer back. A queue follows the first in first out principle and uses 2 pointers, one for the first item that was added and one for the last. Any new item gets added after the last pointer, which is then updated, and dequeuing starts at the first pointer. Another useful data structure is a hash map, which is just a collection of key value pairs. It works kind of like an array, but uses a hash function to take a key and assign it to an index, where its value is then stored. But sometimes 2 different keys can map to the same index, which is called a collision. There's different ways to deal with this, but one way is to create a linked list at that position in the array, which makes it a little slower to look up that value, but still, hash maps are incredibly useful because you can define the keys that point to every value, and since they're based on arrays, retrieving them is blazingly fast. For many problems, it can be very useful to represent the relationship between different data points as a data structure. If you take the nodes of a linked list but allow any node to point to any other node, you get a graph, where the nodes are connected by edges that can be directed, undirected, and can even carry a weight, which can stand for any metric such as distance or cost. Graphs are useful for analyzing groups inside networks or finding the shortest path between 2 points, for example in Google Maps. There's 2 main ways to search a graph. Breadth first search starts at one node and moves out layer by layer until it finds the target node for the first time. Depth first search explores every single path fully until it reaches a dead end. Then it backtracks to the last node with a different path and continues from there in the same way until it finds the target node. A graph where any 2 nodes are connected by exactly one path is called a tree and represents a hierarchy, for example the file system on your computer. A tree starts at the root and branches out into subtrees which end in leaf nodes. Parent nodes can have any number of child nodes, but oftentimes binary trees are the most useful. For example, a binary tree where all the values left of any node are smaller and all the values right of it are greater is called a binary search tree, which makes finding specific values super fast. If you want to find a target value, just start at the root. If the target is smaller than that node, go left. If it's greater, go right, and repeat this until you find the target. What we just used is a very simple algorithm, which is just a set of instructions that solves a problem step by step. The simplest way to write an algorithm is in the form of a function. It takes inputs, does something with them, and returns an output. Just like variables, you can then call a function by its name and pass in different arguments. When calling a function, the function call gets pushed onto the call stack, which is short-term memory used for executing code, and as the name implies, it's based on a stack data structure, which means last in, first out. To implement algorithms, you often have to compare 2 values, which you can do with operators like greater than or equality, and logical expressions such as and, or, and not. Expressions like these are simple. They can be true or false, which are the possible values of the Boolean data type, and allow you to write conditional statements. If some condition is true, do this, else do that. Booleans can also be used to loop over certain parts of code. One way is with a while loop. While this condition is true, this code will execute. Another way is with a for loop, which can iterate over every element inside a data structure like an array, but can also loop for a specific number of iterations by setting a starting value, incrementing it after each iteration, and setting an upper bound with a condition. Functions can also call themselves, which is known as recursion. This is useful when a problem can be broken down into smaller identical problems, such as calculating 5 factorial, which is just 5 times 4 factorial, which is just 4 times 3 factorial, which is just... But by default, a recursive function will just keep on calling itself forever. This means that it keeps pushing more function calls onto the call stack until stack memory is exceeded in a stack overflow. That's not optimal. To stop this, you have to add a base condition to a recursive function which defines when to stop. Only then will the function calls be executed without crashing your PC. Recursion is cool, but it can be pretty expensive time and space-wise. So, to minimize the amount of computations needed, past results can be saved in a cache, so if they come up again, the computer doesn't have to recompute them from scratch. This is called memoization. Speaking of performance, to judge how good an algorithm is, you can look at time and space complexity, so how much time or space is required to run it. This is measured in Big O notation, which describes the relationship between growth of input size and number of operations needed to execute the algorithm. For example, adding 1 to every number inside an array is O of n, because the number of operations increases in a linear way as the array grows. What's relevant is not the exact number of operations, but rather the trend as the input size goes to infinity. You see, something like n factorial grows way faster than any linear function ever could, so as long as the time complexity is some kind of linear relation, it's simplified down to O of n, and the same thing goes for any other group. When writing an algorithm, there's always different approaches. A brute force approach would be to simply check every item until we find a target in a list, but if you want your program to run faster than a garden snail, you need a more sophisticated approach like divide and conquer. For example, in binary search, you repeatedly check the middle element to see on which side the target is and keep searching in that half until you find it. Also, there's different approaches to writing code in general, which are called programming paradigms. Declarative programming describes what the code does, but not how exactly the computer should do it, whereas imperative programming explicitly describes how the computer should achieve a result with detailed instructions. An extension of imperative programming is object-oriented programming, where you can define classes as blueprints for objects, which are single units consisting of data in the form of properties and behaviors in the form of methods. To code a class, you begin by defining the properties as variables and the methods as functions. After encapsulating properties and methods in a class, you can instantiate an object and use the dot notation to work with its properties and methods. Classes make it easy to organize and reuse code because you can define subclasses that inherit properties and behaviors of a superclass but can also extend and override them. For example, a rubber duck subclass might implement quack with a squeak instead. As a result, rubber ducks can be treated as objects of the duck class but behave differently when quack is called, which is the concept of polymorphism. But for some problems, none of these traditional paradigms will work. Let's say you want to make a computer recognize which of these images is a bee. The problem is, you can't really describe what a bee looks like with code. This is where machine learning comes in, aka teaching a computer to do a task without explicitly programming it to do that task. First, you need a lot of data, which you can split into training data and test data. Next, you choose an algorithm that can change its parameters over time. For example, a neural network where the weights can be updated to achieve a different result. By feeding lots and lots of training data into this algorithm, you can build a model whose accuracy you can then check with the test data. If it's not quite right, the model can improve over time by comparing the output to what it should have been, capturing the difference in an error function and tweaking its parameters to minimize the difference. But no matter how futuristic, bleeding edge, blazingly fast, and optimized it is, if you want people to actually use the application you wrote, you should probably know about the internet. It's a network of computers from all around the globe connected by wires. Like, literally, the internet is just a bunch of thick cables that run at the bottom of the ocean along with facilities like internet service providers that connect you to your destination. These computers communicate with the Internet Protocol Suite. Every computer on the network has a unique IP address, and two computers can then transfer data with a transmission control protocol. It breaks messages into a bunch of packets, sends them through a network of wires before the receiving end puts the message back together. If you have a poor internet connection, you might have experienced packet loss, which is just if some of these packets get lost along the way. If the internet is the hardware, then the web is the software, which you can use with a browser. Every page on the web has a URL. When you type it into your browser, it looks up the IP address of the server hosting this website with a domain name system, which is like a dictionary mapping domain names to IP addresses of actual servers. After connecting to it via TCP, your browser, called the client, uses the hypertext transfer protocol to send an HTTP request to the server, which then gives a response ideally containing the contents of the web page. The actual website most often consists of 3 parts. An HTML file contains all the content of a website and is basically just a collection of elements, which can be text, links, buttons, and so on. A CSS file controls the visuals and makes a website look nice. But a website is useless if pressing nice looking buttons does nothing, so a language like JavaScript adds functionality. But sometimes things can go wrong. With every HTTP response comes a response code, which carries information about the status of the response. For example, 200 means OK, and anything starting with 4 is an error, the most famous one being 404 page not found. HTTP requests can carry different methods, for example get, post, put, and delete, so retrieve, add, update, and delete information. These are often used by application programming interfaces, which connect to applications and allow them to interact with each other, for example store and retrieve data from a database. The most common type of database is a relational database, which uses tables to store data. Columns of a table contain different attributes, and rows represent individual data points. Also, each table has one unique attribute called the primary key. A foreign key is the primary key of another table, establishing a relationship between the two. In this case, each book is connected to an author. With a language like SQL, you can write statements to work with data from these tables. You could look up the titles and authors of all books whose title starts with an H, but for that we have to join the authors table with the books table on the matching key to combine two attributes from different tables into one, giving us this output. These statements are useful, but you gotta be careful or you might just delete an entire database with one line of code. But don't worry, that's never happened before. Behind every login page is a database with usernames and passwords. When a user tries to log in, an SQL query is often used to check if the user input matches with an entry in the database. That's good, but a devious actor could type something like this, which changes the query by terminating the string early and commenting out the rest, which means as long as this username exists in the database, access is granted. This is called an SQL injection attack, and it's one of the easiest ways hackers get places they're not supposed to. Hearing about these concepts is one thing, but to really learn them, you have to see them in action and use them yourself, which is exactly what you can do with Brilliant, which has thousands of interactive lessons for everything from math and data science to programming and AI. They make knowledge stick with visual lessons and interactive problems, which is not only fun and builds intuitive
So ChatGPT just released its
Hello. I lost. I've been doing this for a while. I'm not sure what to talk about though. I've been doing this for 3 hours. It's so fun. uh, Ramen. Tasty. It was cool. Uh, yeah, that's all for ramen. The checkpoints mode, so if I get to any big area in the obby, I should have like a checkpoint there. But this is a big area, so there's no more checkpoints in this area. So I did the entire 95 jumps here. It's so fun. I forgot where to go. I typed it out. Message to all my subscribers. Thank you. It's a lot of subscribers. My last channel had like 150, so it's like more than double. I mean 140. It's like more than double than the last. So yeah, that's cool. I really appreciate it. Oh, yeah. It's so goofy. I forgot where to go. Is it this way? Oh yeah. I think probably if I fail again, I'm just gonna go to practice. I've been failing a lot. Make spots that I shouldn't fail, so I definitely need some more practice. Doing 8? No, probably not. Oh, I forgot to. Okay. I'm gonna go to the practice place. You can join 4 if you want. Okay. This lobby is so massive. Okay. Massive. Why am I only doing good in practice mode? That's silly. Okay. Yeah, I don't know why I'm locked in during practice mode. Like, why not the actual, like, obby? Legit obby. I should probably take a break and play another game, but the devoid grind. It took me like 4 hours to beat it. I mean, the prison last time, or the only time I beat it. It's more than it's been like 4 hours so far. Oh, I normally do that first person. I don't know how I did it. With shift lock. Hmm. Okay. I don't know what music I can play on stream, which is not copyright, so I'm just gonna play it to myself. Oh yeah. God. I don't know, I'm struggling on this jump. It should be easy. Okay. Right, is that one of the devs? Hmm. Three watching. Good night. Okay. Thank you for watching. For watching. For checkpoints mode scripting. Oh, kind of dumb. Go. Two ice block. Okay. Oh my god. Let's go. Hmm. What? Not. Oh, the timer. Yeah, it's pretty easy. The hard part is like below it, the actual prison. Please watch my stream then. Oh man. I hate the two-stud like those squeezes. Goofy. It'd be cool if I can add like a little like notepad little thing to each jump. So I can like remember what to do, like take a long jump and then turn. But that's not how Roblox works. You can't add notepads or notes to jumps. Been streaming for almost 5 hours, bro. 4 hours, 52 minutes. Am I cooked? This jump is so goofy. Yeah, wait. I'm spectating. I suck at the prison. I'm just trying to get like practice so when I do checkpoints mode. I like how in checkpoints mode, like at the prison, you can just like swap to practice and swap back. It doesn't change anything. You don't lose progress. I should probably use first person more. I keep like failing because I don't know where to go in the air. In first person, I could see, kind of. For what? I'll probably go back to checkpoints mode soon. Hopefully I fluke it. I'm not sure how long I want to stream though. It's already like 2 a.m. I'll probably do better if I get if I'm not tired. Right now I'm tired. I'll probably be able to like go log in. Okay. Goodbye. Thank you for summoning the the 2 ice cubes and the boulder. The 5-hour mark is in 5 seconds. Thank you. Okay, it's now 5 hours. Let's go. I'll probably do like 2 or 3 good runs. Yep. Thank you. The spirit of the almighty developer. I'm probably just gonna end it like here instead. Bye bye.